Welcome back, Physical Science 20. This is the first booklet in the FC3 section, 7.1, mole ratios in chemical equations. So all that we've learned up to this point will be applied here, looking at equations and looking at mole ratios, and eventually getting to a point where we can, if we know the amount of one substance, we can figure out the amount of other substance in a balanced chemical equation. So first of all, here it talks about an equation being similar to a recipe. We know the ratios in which elements or compounds combine. So for example, when forming water, hydrogen gas and oxygen gas always combines in a 2-to-1 ratio. So whatever I have for oxygen, double the amount of hydrogen, or vice versa. Whatever I have of hydrogen, half as much, the 2-to-1 ratio, multiplying effects. I get 2 moles of water being produced. So 2 moles with 1 mole, 2 moles. Or if you look here, 2 molecules for every 1 molecule makes 2 molecules of water. Okay, and there's a little visual there. Another, keeping in mind the idea of ratios, and there's a simpler analogy here you could look at as well, and it's making s'mores here. So for example, if you took 2 graham crackers, and if your s'more has 4 chocolates, 1 marshmallow, for every 1 s'more you need 2 of these, 4 of these, and 1 marshmallow. Okay, and of course it doesn't take rocket science to realize that the individual masses of these, which could be considered the reactants, is equal to the total mass of the s'more that you make over here. Because nothing's being added, nothing's being subtracted, just things are being rearranged and put together. So total mass equals total mass. And that has to hold true. The law of conservation of mass suggests that total mass of the reactants, or what you start off with, must equal the total mass of products, or what you end up with. Okay, so fairly straightforward. So if we go back to the water example, 2 hydrogen molecules combined with 1 oxygen molecule to produce 2 water molecules. So their ratio, so if I had, 2 to 2, if I had 4 hydrogens, the balanced equation tells us that for every 2 I need 1. In other words, half as much. So if I have 4, I need 2. If I have 50, I need 25 oxygen. If I have 2,000 hydrogens, I need 1,000 oxygen. If I have 10 moles, I need 5 moles. So it's always 2-to-1. Whatever I have for hydrogen, I have half as much oxygen. And then when figuring out water, if I'm looking at comparing it to H's, for every 2 molecules of H, I get 2 molecules of water. So the ratio is identical there. 2 to 2, 4 to 4, 2,000 to 2,000, 10 moles to 10 moles. If I'm comparing oxygen to water, for every 1, I produce 2, double the amount. 1 to 2, 2 to 4, 25 to 50, 5 moles to 10 moles. So the balanced chemical equation tells you how all of these combine to make the product, or how they relate to one another. Okay, and that's really important to get that idea down, that concept down of mole ratios. So if we look here, the ratio in the amount of moles of one chemical to another in the chemical equation is called the mole ratio. It describes how things interact, etc. So if we go down to this example here, we have ammonia breaking down into hydrogen gas and nitrogen gas. So the balanced equation tells us that we have 2 moles, for every 2 moles of ammonia, we get 1 mole of nitrogen gas and 3 moles of hydrogen. And if you did the balancing here, you'd see that we have equal numbers of nitrogens and hydrogens on each side, not violating the law of conservation of mass. So the ratios here, when the question says here, what amount of hydrogen is produced when we have 5.2 moles of ammonia? So we're relating ammonia to hydrogen. So according to this chemical equation, we could get 2 conversions there. So we have 2 to 3 or 3 to 2. So as you can see here, I'm illustrating that. 2 moles of ammonia to 3 moles of hydrogen. This is how you would have written a ratio in one of your earlier math classes. For chemistry here, we like to think of that as a conversion. 2 moles over 3 moles, and being more specific, 2 moles of ammonia over 3 moles of hydrogen, or flip that around, 3 moles of hydrogen over 2 moles of ammonia. So I can use those two separate conversions. The trick is to figure out which one you're using. So if I'm starting off with ammonia, and if I'm going to hydrogen, of course what we have to do there, we're starting with the moles of ammonia. In order to cancel things, we have to have moles of ammonia on the bottom, and where we're going to in the equation is moles of hydrogen, so that's on top. So we're using this version, 3 over 2. 3 over 2. 3 moles of hydrogen is produced when 2 moles of ammonia react. Cancel, cancel. 5.2 times 3 divided by 2, 7.8 moles of hydrogen. So the mole ratio is used to go from one substance to another to see how they interact in that equation. And the example just goes through that. I highlighted the answer there, and that's how they come together. If we look at this one, a freshly exposed surface of aluminum quickly reacts with oxygen to form a layer of aluminum oxide. What amount of oxygen is required to completely react with 6.4 times 10 to the minus 2 moles of aluminum? So we know the balanced chemical equation here. We can see 4 aluminums plus 3 O2s yield 2 Al2O3s. So it was nice enough to give us the equation. And this time the question is not concerned about what's produced. It's just simply looking at how these two interact. How do aluminum and oxygen interact in terms of moles? So we're told we have 6.4 times 10 to the minus 2 moles of aluminum, and of course the ratio here is 4 to 3. So here we have our two possibilities, 4 moles over 3 moles or 3 over 4, but since we're starting with aluminum going to oxygen, we're going to be using this one. Moles of aluminum on the bottom, moles of oxygen on top. So over here, if we start off with, I guess I didn't work out the answer here. If we take a look here, 6.4 times 10 to the minus 2 moles of aluminum, and we're going to oxygen, so you can see it's arranged here, moles of aluminum cancel with moles of aluminum, and we're left with moles of oxygen. So 6.4 times 10 to the minus 2 times 3 divided by 4, 4.8 times 10 to the minus 2 is the result. Okay. What I did do here is look at the practice questions. Phosphorus, P4 burns in oxygen to produce diphosphorus pentoxide. What amount of oxygen is required to produce 0.25 moles of product? So the tricky thing here is just interpreting the question. What is the question mark? What are they asking you to find out, and what is given in the question? So we're going from P2O5 to O2. So of course our mole ratio will have P2O5 on the bottom and oxygen on top. So if we take a look here, starting off with 0.25 moles of P2O5, and according to the balanced equation, 2 moles is produced when 5 moles of oxygen reacts. So from 2 moles to 5 moles, 2 moles to 5 moles. And of course, you know, if you have it set up right, moles of P2O5, moles of P2O5. So you take 0.25 moles times 5 divided by 2, and we get 0.63 moles of oxygen. Okay, if you look at the next one here, I didn't work through it, but you can. It'd be a good idea for you to work through it yourself to see if you can get it. Iron can be produced from the reaction of iron 3 oxide found in iron ore with carbon monoxide. What amount of carbon monoxide is required to produce 1.4 times 10 to the 3 moles of iron? Okay, so we're starting up with iron and figuring out carbon monoxide. So if I were you, I'd go through that maybe, make sure you're doing okay. And then for the assignment, first of all, the summary, mole ratio, of course, the ratio of the amount of reactants or products in a chemical reaction. The coefficients in the equation determine the mole ratios. So again, you look at the equation and the numbers in front of the compounds. The coefficients help you figure out the mole ratios, relating reactants to products or to each other. And a mole ratio is used to predict the amount of reactant required or product produced in the chemical reaction. Okay, the questions I want you to do: 1, 2, 3, 4. You can omit 5. Question 6. Question 7. Omit 8. Question 9. And for here, there's some quick questions here, just simply filling in the blanks. Figure out the mole ratios that are involved here. So you don't have to show your work if you don't want to, but just simply use the equation and then figure out how many moles that you will require here. And but for these ones here, you do have to show your work in order to do that. Alright, so I think that should be it. I don't think there's anything tricky in this assignment. A little hint here, how much products are expected, and of course by products we mean what's on the right hand side, magnesium hydroxide and ammonia. Otherwise I think this is fairly clear cut. So the questions that we did here, these quick ones here, just simply multiplying by one conversion factor. That's basically what these charts are illustrating here, so you can quickly just simply write the answers. Whereas here I need to see the work for the rest of these ones. Okay, see you again.